All right, so very much related to the SN1 reaction, we're going to talk about carbocation stability. So we've got a methyl cation, a primary cation, a secondary cation, and a tertiary cation right here. So um, again, this is really important for SN1 reactions, and we'll see that later after we start talking about the Hammond postulate as well. But as we go from left to right, we have an increased carbocation stability. And this increase can be seen, or it can be explained by two factors. One is the inductive effect, which we have seen before in acid-base chemistry, and the other is hyperconjugation, which is something we haven't seen before. Okay, so let's talk about inductive effects first. So inductive effects, again, we saw this in acid-base chemistry. So for example, let's say we have this carboxylic acid, and we've got a chlorine right there on the alpha carbon versus the chlorine on the beta carbon. Which one is more acidic? Well, it's the one on the left, right? And that was because that chlorine was basically closer to the negative oxygen, or the site where the proton leaves, okay? And that was because of inductive effects and the electronegativity of that chlorine basically withdrawing electron density through sigma bonds, okay? So that's the idea of inductive effects, electronic effects through the sigma bonds. Okay, so we have those arrows representing the flow of electrons through the sigma bond, okay? Now that's the reason why that's useful for explaining the carbocation stability is because instead of electronegativity withdrawing electron density, we have the opposite effect in this case. So first, the protons in this methyl carbocation, they're lame. There's not too much electron density, and so there's nothing going on in this case. But once we start having R groups on that carbocation, carbon, there's more electron density here, right? And so that allows for the donation of electrons through that sigma bond to help stabilize that carbocation carbon center. Okay, and so the way that I like to think of this is carbon and carbon, they're the same atom, they have the same electronegativity, and so they like to be equal to one another. And so if one of them is positively charged and the other is neutral, then I think of it as the carbon being more willing to share its electrons because it is the same, and so they want to equal the same value more or less, and so it gives electron density through its sigma bond. Okay, so R groups are considered electron donating groups, and I've drawn all the red arrows to kind of show you that flow of electron density into the carbocation. So now what that means is we have an arrow going from left to right. Since we have an increase in the number of R groups going from left to right, we also have an increase in carbocation stability, okay? And again, that's all about inductive effects. Just R groups are electron donating groups in this case, okay? Let me write that here, inductive effects. Okay, so that allows us to move on to hyperconjugation. Okay, so hyperconjugation it's actually kind of a cool concept or idea. It's really all about stabilization of carbocations by having so remember, those carbocations have an empty p orbital, so that empty p orbital overlaps with an adjacent sigma bond. And so the only way that it's going to have that adjacent sigma bond to overlap is if there's a carbon there instead of a hydrogen. So let's take a look at what I mean by that. So this is an example of a methyl cation. We have that hydrogens with the s orbital kind of just chilling there, all teeny tiny, and that p orbital poking up and down. Okay, so let's say we had a primary carbocation. So we've got two hydrogens on one side, and we've got a carbon let's just say there's hydrogens on, it's a methyl on this, so there's 3 hydrogens here, and so now we have that p orbital sticking up and down, right? Now that p orbital can overlap with that adjacent CH bond that's kind of sticking up here. Okay, so the electron density from that carbon hydrogen sigma bond overlaps with that adjacent p orbital, and essentially providing electron density to help stabilize that carbocation. Okay, and so this is the case for a primary carbocation, right? Well, what if there were more? Well, if there's more R groups, then that means that there's more stabilization through hyperconjugation, right? Because we're going to get that from all sides, and that means one carbon has to donate less to help stabilize that carbocation center, and so everybody's going to be more happy. That's why the tertiary carbocation is more stable. It's going to be a combination of inductive effects as well as hyperconjugation. Okay, but who cares? Why are you even talking about this? Here's me on a scale of caring. I'm at 0. Yes. So let's think about what we've talked about. We've talked about basically carbocation stability. Before that was SN1 mechanisms, and before that was SN2, right? So SN1, remember, has the 2-step process where we get the carbocation intermediate. So the SN1 rate of reaction increases with increased number of R groups, right? And so why would that be? Interesting. Well, that was kind of a similar thought process for the carbocations, right? Well, let's say we have all these variety of R groups, or I'm sorry, a variety of substituents. Substrates. Haha. And we have an increased rate of SN1 reaction as we go from left to right, right? So that's a methyl all the way up to tertiary. Well, we also, let's go ahead and, I'm going to copy and paste this. Do you ever feel like when you're doing certain things, you're trying to take shortcuts, but it actually takes a lot longer in the end? I probably could have just drawn that out, but I'm going to do this anyway. Yep. Definitely could have drawn this out by hand again. It would have been much faster, but, I feel good. I still feel good about it. I made the right decision, y'all. All right. So we've got the methyl primary, secondary, tertiary carbocation. As we go from left to right, we have increased stability of the carbocation, right? Well, that's oddly familiar. Let's say that the leaving groups all left. What would we get? Well, what we're going to get is these respective carbocations down below. Well, what does that mean? Well, let's think about what that means. So if you look at the top set of reactions, those are increased rate of an SN1, right? And then we have increased stability of carbocation for the other one. So that means that the rate of the SN1 reaction increases, the stability of the carbocation increases, okay? So that means we're talking in terms of rates of reactions, that's activation energy, right? So, and then in terms of stability of carbocations in this case, that's delta G, okay? So let's try and mash those two together in a concept called the Hammond postulate. So the Hammond postulate provides a qualitative estimate of the energy of a transition state, okay? So what that means is that we are able to, if we are able to predict the energy of the transition state, okay, then that means that we should be able to predict the relative energy of the, or the activation energy, because that's pretty much if the same value, right? And then that means that we should, in theory, be able to predict the relative rate of the reaction. Okay, so that's how this all ties in together. Okay, so there's also the other point: transition state of a reaction resembles the structure of the species, the reactant or the product, to which it is closer in energy. Say what now? What you talking about, Jess? Well, let's take a look-see. What do I mean by that? In picture form. Everybody loves pictures, right? Pictures are just so much better than words. I'm not gonna lie. Actually, some say pictures are worth 1,000 of them. Teehee. All right. So anyway, here's two gorgeous energy diagrams. We got the energy on the y-axis, and the reaction coordinate is the x-axis. So you should know that stuff already. Should be pretty easy to do. The reaction on the left is endothermic, and the reaction on the right is exothermic, right? Because the products are higher and lower in energy, respectively. Okay, so these are our transition states, right? Now, the transition state represents the species that is closer to energy to. So for the endothermic reaction, that means that the products are closer in energy to the transition state, and then for the exothermic, the reactants are closer in energy to the transition state. Okay, so remember, we're comparing on the y-axis, so the products are closer to the transition state in the endothermic reaction, and so the endothermic transition state looks like the products. And then for the exothermic reaction, the exothermic transition state looks like the reactants. Okay, so why, hold on, right? Reactants. Okay, so why is this important? Well, it helps us kind of make that qualitative assessment on the transition states, and in turn that allows us to determine the rate of a reaction based off of the energy of the products, or in this case the reactants, right? So here we go. If we have a lower energy products, then we have lower energy transition state, and that's going to be for the endothermic reactions, right? Now, if we have higher energy products, then we have higher energy transition state. Okay? And so remember, high energy transition state means high activation energy. And low energy transition state means low activation energy. And that's where the rate comes in. Okay? So let's draw out basically a blue and red curve representing those words. Okay? So the low products have the lower transition state, and the higher energy products have the higher transition state. Okay. Now we can visually see that if we were going to draw in the activation energy of these particular curves, then we would see that that activation energy would be much lower for the red curve, which has the lower energy products. And there you go. So endothermic reaction, or in endothermic reactions, the more stable product forms faster. And that's because it has a lower energy transition state, okay, and therefore a lower, scrabble, activation energy, okay, EA. And there you have it. We've tied everything all together. That makes it a faster reaction. Okay? So that's for endothermic reactions specifically. Exothermic reactions now are a little bit different. Here's the fun part. Okay? So let's say we've got a red and a blue curve again. The reactants, they're starting from the same reactants. They're equal in energy. And let's say we have our products. Let me move that lower so it's a little bit easier. So get red has a higher energy product than the blue curve, but they're still lower in energy than the reactants. So this is still by definition an exothermic reaction. Okay, so now here's the transition state. I haven't drawn it in yet, the energy level, but it looks like the reactants, which are the same, right? And so that's because reactants are closer in energy to the transition state. So the blue and the red curve are going to be at the same point, and so when we draw on our red curve, we reach the same peak as we do when we draw our blue curve. Okay, so there is our activation energy. Our activation energy for the red and the blue curve is actually the same. Okay, and so what that means is we have the same relative reaction rate for the red product and the blue product. So for exothermic reactions, we may or may not form the lower energy product. And that's because we still have the same activation energy, because the transition state in an exothermic reaction represents the or it looks like the reactants, and has that is the energy of it is therefore dictated by the reactants, which in this case are the same. Okay, so it's important that we put that in your brain, write it down, think about it. So this is the case, is our scenario. This is representing a scenario where we can have two possible products in a given reaction. Now what we need to do is think about the energy levels of those transition states, if it's endothermic or exothermic, etc. Okay. All right, so now let's think back to this one, right? So this is actually the first step in an SN1 reaction. Okay, so that blue curve, that higher energy curve, would actually represent the carbocation, let's say a secondary carbocation, while this lower energy red curve could represent the tertiary carbocation, right? So this is the more stable carbocation, and it's also going to lead to a faster reaction. And now we know why, because of the stability of that carbocation and its relationship to the transition state. It's going to have a lower energy transition state. Here's an SN1 curve, and if you slice it right down that middle of that, where that intermediate lies, that's kind of what we're looking at. That first portion right there that I'm drawing in that beautiful purple color, that is the endothermic portion of this particular reaction. Okay, and so that's pretty much it for carbocation stability in the Hammond postulate. So it's gonna take some thought. You're gonna need to think about it, put some more work into this, and also maybe even watch it again. Okay, let me know if you have any questions.